All right, so what we're going to talk about now is integration by u-substitution. I'm sure you can find some good videos online to supplement this, but I kind of wanted to go through a few examples so you kind of see how it works. Now really what we're doing is we're undoing the chain rule. So undoing the chain rule of differentiation. So you might remind yourself that the derivative of f of g of x dx, not dx, is equal to f prime of g of x times g prime of x. So what we're going to be looking for then is basically the antiderivative of f prime of g of x times g prime of x. If we have the antiderivative of this, then we can just have f of g of x. And what we're going to do is basically let u be g of x, and g prime is going to be du, and we can basically simplify it into something that is easier to integrate. So let's look at basically a few examples of u-substitution, which is really what we want to do here. So for instance, let's say we had the antiderivative of 3x squared cosine of x cubed dx. Okay, so what we see is we see a composite function where the inner function's derivative is also there. So this is what we're going to let be our u. U is going to be x cubed. So du dx, the derivative of u with respect to x, is simply 3x squared. But what we're going to write is du equals 3x squared dx because we want to write this in terms of u. So everything has to be in terms of u. So the x cubed has to be in terms of u, which it is, and the 3x squared dx has to be in terms of u, which it is. It's du. So this is now the antiderivative of cosine of u du. But that is just simply sine of u plus c, right? We know how to find the antiderivative of cosine of u. It's just sine of u plus c. And now we want to plug back in our u and say, oh, that's going to be sine of x cubed plus c because u is x cubed. Now, if we check our answer by taking the derivative, which we won't do most times, the derivative of this is cosine of x cubed times the derivative of x cubed, which is 3x squared. So boom, that's exactly what we want. We've done u-substitution correctly. So again, we are finding the inner function, letting that be the u, taking the derivative of both sides so that we get the dx in terms of the du, right? This basically tells us the relationship between how much we wiggle x and how much we wiggle u. So u depends on x, but its derivative depends, its change depends on the change in x times 3x squared because of their relationship. So that's fine. Let's try another example. So say we take the example of t e to the t squared plus 1 dt. Now again, not really sure how to anti-differentiate this immediately, except that I see t squared plus 1, and I know the derivative of that is 2t, which is a multiple of t. So it doesn't have to be exactly the same as long as some multiple of that derivative shows up here. So let's let u be t squared plus 1. Then du is simply 2t dt. Now, what I have is not 2t dt. I have t dt. So, fine, I'll just simply divide both sides by 2 to get t dt. So now, this is 1/2 du, and that is u. So the 1/2 will go out front, 1/2 times the integral of e to the u du. And I always want to make sure there's the 1/2 du, that matches up with the t dt, and there's the e to the u, which matches up to the e to the t squared plus 1. Now it's just anti-differentiate normally, 1/2 e to the u plus c, which is simply 1/2 e to the t squared plus 1 plus c. So of course, if I took the derivative of this, I would end up multiplying by 2t, and that would give me the t. Hooray! Okay, let us try the antiderivative of x cubed square root x to the fourth plus 5. And of course, if you're not doing this, good to pause and try this on your own. What is u going to be, and how are you going to find this antiderivative? But we're going to let u be x to the fourth plus 5. That's the inner function. Its derivative is a multiple of x cubed. So we'll get du equals 4x cubed dx. But we don't have 4x cubed dx. We have x cubed dx. So we will do du over 4 is equal to x cubed dx. So this becomes 1/4 times the integral of root u du, right? 1/4 du is x cubed dx, and root u is that. So this is simply 1/4 integral u to the 1/2 du, which is 1/4 u to the 3/2 divided by 3/2 plus c, which is multiplying by 2/3. Boy, that's going to be like 1/6 u to the 3/2 plus c, which is 1/6 x to the fourth plus 5. I don't know why I wrote plus twice. All to the 3/2 plus c. This should just be one giant plus. Okay, that seems reasonable. So this is the basic idea between u-substitution. Let's see if we could look at a definite integral, right? So what's going to be different if we have a definite integral instead of an indefinite integral? So let us take this as an example, the integral from 0 to 2 of x e to the x squared dx. Now again, this looks like a u-substitution problem because there's the inner function x squared and a multiple of its derivative x. So let us let u be x squared, and let us let du be 2x dx. Thus, du over 2 is dx times x dx, right, which is what we have, x dx. Now, because this is a definite integral, these are x values, right? This is x equals 2 and x equals 0. But we're trying to write this thing in terms of u, which means we need to change those to u values. So if x equals 2, then u equals 4. And if x equals 0, then u also equals 0. So we have to make sure to change our limits of integration so that they match the variable we are integrating with respect to. And this is going to now become the integral from 0 to 4 of 1/2 e to the u du. And now I never have to go back to the x because I've changed everything into the terms of u. So this is going to be 1/2 e to the u evaluated between 0 and 4. These are u values, so I can plug them straight in. This becomes 1/2 e to the fourth minus 1/2 e to the 0, which is 1/2 e to the fourth minus 1/2. And that should be a fine answer. So remember to change your limits of integration. We can't go from 0 to 2 if we're integrating with respect to u because those are x values. There's some other kind of interesting stuff which we might want to consider and see if we can kind of figure out. So let's take a look at some other examples where it's not immediately apparent what we should do. So let's take this as an example. What if you have the integral of x times the square root of x plus 2? All right, so this is a little different because what we have here is we have an x plus 2 in a root here, and then we also have an x. We can't multiply this through because of the addition inside the radical. There's not exactly an inner function and its derivative, but the inner function and what's outside are basically the same thing, right? They have a linear relationship, x plus 2 and x. So you can still let u be x plus 2, and then du is dx, okay? But we also need the x in terms of u. So what we can do is say, well, you know what? X is actually u minus 2. And this is going to help us out because now the subtraction or addition is outside the radical, and that will help us to basically distribute. So this is going to become the integral of, now x, remember, is u minus 2. Square root of x plus 2 is just square root u, and dx is du. Now you may be thinking, well, that didn't really help us, but it did because now we can distribute this. We couldn't distribute through the radical, but we can distribute now, and that just becomes u to the 3/2 minus 2u to the 1/2, and oh my goodness, now we have something that the power rule applies to. So this often happens with a linear function and another linear function, and we can end up getting u to the 5/2 times 2/5 minus 2u to the 3/2 times 2/3 plus c, which ends up being 2/5 u, which is x plus 2 to the 5/2, minus 4/3 times x plus 2 to the 3/2 plus c. So watch out for those problems where you actually have to substitute for x as well. Well, let's try one more problem, and then we'll call it good for integration by substitution, and we'll let you practice it. So how about the integral from square root 1 plus root x dx? Oh my goodness. Well, this doesn't look super good, but maybe we can figure it out. Who knows, but might be nice to try if u is just the inner function 1 plus root x. Now, if u is 1 plus root x, then du is 1 over 2 root x dx. Oh man, now this is very confusing because I don't have the root x. Oh, but wait. If I multiply both sides by root x, then du root x is equal to 1/2 dx, and furthermore, 2 times du root x is equal to dx. But root x is u minus 1. So this is actually 2 du times u minus 1. That's dx. Ugh, that's awful. But I now have dx in terms of u only, where I didn't before, and I have this in terms of u. So this actually becomes the antiderivative of the square root of u times 2 du times u minus 1, which is simply 2 antiderivative of u to the 3/2 minus u to the 1/2 du. Oh my goodness, that would take some creativity to get that problem, but it looks like that might work. And then you could integrate that. So maybe one more, just for fun, just to do one more example here, and then we'll cut it off. So what if you had this one? The antiderivative from, say, 5 to 10, so this isn't the antiderivative now, but the definite integral, of x plus 7 times the cubed root of 3 minus 2x dx. Oh my goodness. Linear, linear. So I'm going to let the inner linear function be my u, and see if I can write the other one in terms of u. So if u is 3 minus 2x, then du is negative 2 dx. Okay, I just have dx, so that means du over negative 2 is equal to dx. But I also know if u equals 3 minus 2x, then u minus 3 equals negative 2x, and u minus 3 over negative 2 equals x. So I can plug that in for x here, and I will have that. I also need to change my limits of integration. So if x equals 5, u is equal to 3 minus 10, which is negative 7. And if x equals 10, then u is equal to 3 minus 20, which is negative 17. So this is going to become the antiderivative, rather the definite integral from negative 7 to negative 17 of x, which is u minus 3 over negative 2 plus 7, times the cubed root of u times dx, which is du over negative 2. And that is going to become negative 1/2 integral from negative 7 to negative 17 of u minus 3 over negative 2 plus 7 times u to the 1/3 du. Now I'm going to stop there, but you could algebraically multiply these out, and you'd have some very nasty thing, but theoretically it's possible. So that is u-substitution. Have fun with some of those problems.